So today in this video we'll talk about Maxwell-Boltzmann statistics. Basically we'll try to cover some more topics on classical statistics which we could not cover in the earlier videos while discussing classical statistics. So the main aim is to talk about here Maxwell-Boltzmann energy distribution law or distribution function, and then another one is the degeneracy parameter. Okay, so these are the topics which are not directly included in your syllabus. However, these are the topics, or as you will see in this lecture, that this will be used of extensively in while discussing quantum statistics. Okay, so you may think about this, whatever you are going to learn in this lecture is a prerequisite for quantum statistics, which we are going to discuss in videos after this. Okay, so we'll start now. Okay, so we shall talk about this Maxwell-Boltzmann statistics. So let us now consider a thermodynamically isolated system of n particles, okay, and which is at constant temperature, constant volume and pressure. Okay, so this is a thermodynamically isolated system, and then it has got constant pressure, temperature and volume. So of course its energy will be constant. So the energy of the system is, so the total energy of the system is constant. Okay, and let's say so as I said, there are capital N number of particles. So the energy levels which are available for this particles in the system is, let's say, E1, E2, E3, so on and so forth. Okay, and moreover we can say that these energy states may be quantized or continuous. Okay, actually these are quantized. Okay, these are discrete energy levels. However, when these energy levels lie very close to each other, then we can assume these to be, that energy values to be continuous. Okay, so moreover I would like to draw your attention that in the earlier videos, while having a discussion on classical statistics, you must be remembering that while discussing about this microstate, macrostate, we considered that n number of particles being, we have to distribute in various compartments of one's equal size, unequal size. Okay, so here you will see the connection with the realistic system. Okay, so by applying the concept of equal a prior probability, we have used how to have the distribution of number of particles into equal compartments, and if you don't have the equal compartments, then we introduce a concept of cell. Okay, so then we made the unequal compartments, okay, into various number of cells, but cells are of equal size. So these cells, you will see that these are quantum states. Okay, you can correlate these two things. Okay, so each boxes or the compartments that we talk about, these are one on energy levels of the system, real system. Okay, and within that you will have some quantum states. Okay, so let's say there are 4 boxes, like the 4 energy levels, and within there we have these cells of equal size. Okay, so these are like quantum states within that energy level. So when you talk about a energy levels, okay, so there are lots of quantum states, let's say. So this is a energy level, and then lots of quantum states. Okay, so you will see as we come along. Okay, now see, these are ideas which we have discussed earlier, but then reiterate, revise, okay, and make familiar yourself with these things. Okay, so suppose at any given instant of time, okay, so you have n1 number of particles which are in the energy state or the energy level E1, n2 number of particles, let's say energy state E2, similarly n3 in E3, okay, and so on and so forth. Okay, so if I take a in general ith state, then which has got energy EI, okay, so number of particles in there is Ni. So I have a macro states. How do I define that macro state? N1 in compartment 1, or I should say here energy level 1, N2 in energy level 2, okay, similarly Ni in energy level I. Okay, so if I have like that, then I can write total number of particles and expressions for total number of particles as well as for total energy of the system. So the total number of particles of the system is given by this expression, and I can shortly write in a sum over I, okay, and Ni. Similarly, the total energy of the system is, because I have to sum up energy of all the molecules, right, or all the particles. So Ni number of particles are there in the level 1, we having energy E1 each of them. Similarly, N2 number of particles are there in energy level E2, meaning, okay, second state you can think about, and having each of the particle having energy E2. So I can sum up all these things, then I will get an expression short form like this. Okay, so I will be using this expression. So let me clean up here. Okay, so now let's assume that there are total number of, let's say, k number of energy levels in the system. Then we know how to calculate number of microstate for a given macrostate, right, which we have studied earlier, which is given by here this W. Okay, W equal to n factorial, then the product of I going from 1 to k, and then this expression. Okay, and GI is what? This number of cells for that compartment. Okay, I. So or you can think about this is like a, so in that energy level, how many quantum states are there? GI number of quantum states. So GI number of cells for the compartment I compartment. Okay, so if you compare, if you relate to that example which we have talked about in earlier videos. Okay, so here for the energy state, let's say EI, so there are how many quantum states are available? Like this, in the EI there are GI number of quantum states are available. So to distribute n1 particles in energy level 1, like first E1, there are n2 number of particles in second state, is E2 level. Similarly, so on and so on, up to nk number of particles in k state. How many ways we can arrange these particles? These are classical particles, right? So I will get this expression. This we have derived in the earlier expression as well. And then in statistical equilibrium, what happens? System takes up that macro state which has got maximum thermodynamic probability. Meaning what? It will take up that macro state which has got most number of, or the maximum number of micro state. And this W is what? Number of micro state for a given macro state. That is also thermodynamic probability. So for most probable distribution, we will differentiate, right? So this D ln W equal to 0, we will put up that condition. So W is going to be a really large number. So that's why we'll use this ln. Okay, we take logarithmic value both side, right? And then we'll approximate using Stirling approximation, so which we have studied earlier. Okay, so simply we differentiate this ln W with respect to n1, n2, n3, because we know that W is function of n1, n2, n3, and so nk all the way, right? Okay, so this is function of W is function of n1, n2, n3, ni, and all the way nk. So I can differentiate, but then right hand side I need to equate it to 0. So in short form I will get this. Okay, sum over I going from 1 to k, and del ln W by ln I d ni equal to 0. Okay, so what I will do, I'll mark this as my expression 3. Okay, then since this n is constant, I can take differentiation. If the constant number will be 0, or in short form I can write sum over I d ni equal to 0, and I will multiply this expression by, I'll multiply this expression by alpha. Similarly, this u is a constant, right? If I differentiate, okay, if I take total differential, then it will be equal to 0. In the short notation term, I can write sum over I ei d ni, okay, it will be equal to 0. So what do? Okay, so I multiply this expression by, let's say, beta. Okay, so the right hand side anyway is 0, and I call this is expression 1, this is expression 2. I'll sum up all three of this expression. Okay, see here one thing I think you all remember, that this d and I individually is not going to be 0, but sum of them will be equal to 0, right? Meaning what? In equilibrium, what will happen? These particles may undergo collisions. So what will happen? There will be exchange of energy among the particles. So maybe at some instant what will happen? Number of particles in high energy state, let's say the nearby state, will increase. Okay, so there will be exchange of particles. Okay, then in somewhere the number of particles will decrease. So this exchange of particles among these energy levels will keep going on. However, the total number of particles is constant. So that's why this n, which is if you take differentiation, or if you differentiate, it will be equal to 0. Okay, so now let me just sum up all this expression 1, 2, and 3. So what I will come up? I will get this expression. Okay, so I know that again this d ni, the change of ni, the number of particles in energy level is independent of each other. This N1, N2, N3 all the way Ni, Nk change over this is independent of each other. So the so that's what will happen. This is, we can borrow the concept from the linearly independent expression, right? So this, since D and I, so change of D1 is independent of any one of them, let's say D and K. So what will happen, this expression to hold good, its coefficient, that is this part, should be equal to 0. This is the concept of linearly independent expression, right? So linearly independent expression. Okay, so what will happen, these coefficients what we are talking about right now should be equal to 0. Okay, so then we need to talk about again this ln W, which we have already discussed earlier videos. So using the approximation of, so this Stirling approximation, what I mean to say, this n is going to be really large number, okay, here. So if I take log both side, since I have done in earlier videos, you can go back to that video and watch again. Okay, so ln W will be equal to, will be given by this expression. So here I have used this Stirling approximation as well. If you have n factorial, okay, if you take ln of that, it becomes n ln n. You can approximate equal to ln that. Since n is very large number, you can approximately write this expression. Okay, using all those approximations and other simple algebra that we have done in earlier videos, I will get this ln W will be equal to this, okay, n ln n minus n plus sum over all this expression. Okay, I need to differentiate now with respect to Ni, this expression. So anyway, this part will be, this is a constant term, so it will be, if I differentiate, then it will be equal to 0. And now I come up with this expression. So this term is constant, isn't it? So then if I differentiate with Ni, so I will get on the constant term here. This will be the dni with respect to dni will be equal to 0. Okay, now I come to this expression. Okay, so for that one I keep, let's say first this ln ni constant, so I differentiate this ni, so I minus ln ni, I get it. Then I keep this minus ni constant and we differentiate ln ni with respect to ni. What I will get? I will get 1 by ni. So the ni and I will cancel, I will get minus 1. Then from this I will get simply 1. So I will remain with only this expression. Okay, so if I substitute this, okay, because this equal to this, so if I substitute this expression back here, so I will get this expression, minus ln gi by ni minus alpha minus beta ei equal to 0. Okay, so now if I shuffle these terms left and right, I will get this expression. Okay, so which will give me an expression, this is ni equal to, okay, this gi e to the power minus alpha e to the power minus beta e. Okay, so this is known as Maxwell-Boltzmann energy distribution law in general form, which you have seen in earlier as well. Okay, so Boltzmann canonical distribution type. Okay, so I hope you remember this, but we did not write e to the power minus alpha, we have written e to the power minus lambda, and which we call it a. Okay, and then if we remember, this beta is 1 by kt, which is k is a Boltzmann constant, so I can substitute back for the beta, then I will get this expression ni equal to, so ni represents what? It's a number of particles in the ith energy state, okay, having degeneracy or gi number of quantum states in the energy level I. Okay, so let me continue now. Okay, so now again, since I know this expression, okay, so here you will try to find out this expression for e to the power minus alpha. Okay, this is a very important parameter. Okay, so this n equal to sum over I ni, we know that, so n is total number of particles in the system, and then substituting for ni I get this. Okay, so now and then we will get that, so I need to just simply keep, so this e to the power minus alpha is constant, so it has come out. Okay, so reshuffling again left and right, so we get this expression for that. Okay, now this denominator part is what? This is our partition function, if you remember. Okay, so I'll simply, if I substitute for z and then ni, I will get in this number of particles forming this this form. Okay, so now we will talk about this energy distribution function. Okay, so the general energy distribution function f of ei is defined as the average number of particles per quantum state in the ith energy level having energy ei. Okay, so this distribution function, energy distribution function, is defined as what? Is the number of particles per quantum state. Okay, as you can see here. Okay, so this is distribution function, and then from this the earlier Maxwell distribution and energy distribution law, I get this expression, right? Simply I have to transfer this gi from the right to left, okay, in the denominator, and I will get this expression. Okay, so this f of e is a product of two things. This is two terms, right? E to the power minus alpha, then e to the power minus ei by kt. Okay, so just to make a note here, this distribution function, even though it looks like pretty simple here, you will realize that as we study quantum statistics, or meaning now itself you can see that this gives you some kind of probability of occupancy of a quantum state. Okay, so in classical statistics, what happens? I mean, the GI is because the size of the phase cell can be anything, right? It may tend to 0. So there are a very large number of this GI, meaning the quantum states, or that many states are available, meaning classically. So the number of molecules per state becomes really low. I mean, it could be max 1. Okay, so the probability is become really low. So that's why the number density is really low. Okay, so we will talk about this as we discuss more on the quantum statistics, when we start discussing about quantum statistics. Okay, so now for time being, this energy distribution function is a product of these two expressions. Okay, now let's try to find out expression for this. Okay, so we'll come back to this. Okay, so now if the energy levels of the systems are very close to each other, then we can, as I said in the earlier slides, there we can use the continuum values of energy. So the number of particles, this n of E dE, whose energy, so this energy lies in the range E n E plus dE. So this expression represents what? This number of particles whose energy lies between this E and E plus dE. Okay, so this is given by what? This product of this distribution function multiplied by G of E. G of E is what? Okay, so this expression represents number of states which are available, or the number of states lying in between the energy range, this E and E plus dE. Okay, so the number of particles which are available, or number which are present in the energy range E and E plus dE is a product of two things. That is, one is the distribution function, and another function is the number of states available in that energy range, isn't it? Okay, so from you can sense here this f of e is also represents some kind of probability here. Okay, so okay, now for ideal gas, this e to the power minus alpha is given by this. Okay, now how did I get this? Okay, so we have almost derived this in earlier videos, but let's try to connect these dots. Okay, so in this video, so here you have seen that so here you have seen that this e to the power minus alpha is given by n by z, right? So this is the expression in discrete form. So I can write in continuous form. Let's say energy is continuous now. What I can write, this n by integration from 0 to infinity g of e to the power minus e by kt dE, isn't it? But we have derived a expression for this in lecture number 12, right? You can check, and which I have written here. This is given by this expression. So if I substitute, so the e to the power alpha, so the n by this v by h cube 2 pi m kt to the power 3 by 2. Okay, so what you need to do? Simply I have to right, n by v, and make sure this h goes on top, and then 2 pi m kt, okay, and I just put whole to the power 3 by 2. Okay, this is what your expression is, e to the power alpha. Okay, so kindly go back and check this expression for this. Okay, how did we come about this expression? Okay, we have done a bit of math there. So after getting this e to the power minus alpha expression, then I have to multiply by this term to get this distribution function. Okay, so because here see e to the power alpha multiplied by this term, and in energy in continuous form. All right, so having got here, so we need to, so we are trying to find out the expression for this n of e de. Okay, so we have got expression for f of e, then g of e also we have derived in the earlier video, that is in lecture number 12, where this is given by this particular expression. Substitute back, so this is your f of e, let me just put it here, this is g of e, right? Okay, and now you do a little bit of cancellation here and there. Okay, so this I guess v and v will go off, this term and this exponential term will come as it is, h squared up, because to the power 3 is same, everything will go off, this 2 will go off, m will go off, 2 m, all this will, so this is 1 by pi to the power 3 by 2, and you have a pi here, so it will get cancelled out, and I will remain with 1 by square root of pi, and this 2 will remain, this n will be as it is, and then of course this kt, meaning 1 by kt to the power 3 by 2 will remain as it is. So I will get this expression. So this expression is known as Maxwell-Boltzmann energy distribution law for the particles of the ideal gas. So see, for whatever expression we are dealing with here, or everything is for ideal gas. Okay, all right. So now we'll try to look at this e to the power minus alpha term even more carefully. So we have this expression e to the power minus alpha equal to this n by v h square by 2 pi m k t to the power whole to the power 3 by 2. Okay, so if I just invert, meaning I write e to the power alpha simply, I have to invert this, switch the numerator and denominator, so I will have this expression. Okay, and this expression is known as a degeneracy parameter. Okay, now you have to be a little careful about here. Okay, so degeneracy we have discussed in the beginning part of the video as well. So that degeneracy which we are talking, this GI, okay, that is the energy degeneracy, meaning the number of states or the number of particles which lying in defined quantum states but have similar energy or same energy. Okay, that is energy degeneracy. But this degeneracy parameter is something different. Okay, which we learn now. Okay, so but you need to remember this e to the power alpha, this degeneracy parameter is very important, because you will see this parameter again and again in the quantum statistics when you deal about this ideal, meaning the Bose gas and the Fermi gas. Okay, so this Maxwell-Boltzmann statistics is applicable to a system of particles when the mean distance between the particle is greater than the thermal Dibrugarh wavelength. Okay, so now we have considered n particles in volume V. Okay, so the volume per particle is given by this V by n. Okay, so the average distance I can talk about if I have, because volume is proportional to r cube. So if I take 1 by 3 of this expression, it gives you the mean or the average separation between the particles. Now if this is greater than the thermal Dibrugarh wavelength, which is given by this expression, okay, then we say that this Maxwell-Boltzmann statistics is applicable, or the classical statistics holds good or suited good. Okay, so while shifting this expression left and right, I come about this expression. Okay, and eventually when I take this term to the left hand side, I get this, and this is nothing but your expression for e to the power alpha, which is degeneracy parameter. Okay, now so we come to know that whenever this degeneracy parameter is greater than or equal to 1, or in fact is much greater than or equal to 1, we say that this system so you can apply Maxwell-Boltzmann statistics or the classical statistics to this system, and it will give you better result, or your results that which you calculate through using these statistics will be valid. However, you will see in the case number 2 and case number 3, as we discuss along, your this whatever system you have considered, it will slowly deviate from the ideal behavior, or the behavior predicted by the Maxwell-Boltzmann statistics, it will not follow. Okay, so this degeneracy parameter somewhere gives you an idea of like how ideal is this ideal gas particles, or the ideal particles that we have talked about here, or ideal gas molecules that we have considered here. Okay, so let's go one by one. So in case number 1, when this your degeneracy parameter is greater than 1 or much greater than 1, then we say that this gas is non-degenerate. Okay, and we say that the prediction made by the Maxwell-Boltzmann statistics holds good. Okay, so it's able to predict whatever the phenomena that this gas particles is going to show you. Okay, but whenever this degeneracy parameter is greater than 1, but that not too large, okay, just greater than 1, not very large, then gas is said to be weakly degenerate. Okay, so gas is said to be weakly degenerate, and you will see that the behavior of this gas will slowly deviate from the ideal case, or the ideal gas particles. Okay, now on the extreme case, when you will see this degeneracy parameter, which is e to the power alpha less than 1, then the gas is said to be strongly degenerate. So in that case, you will see that your particles will deviate, meaning deviate more from the ideal behavior of the gas molecules, what we typically see in the Maxwell-Boltzmann statistics. Okay, so these parameters you will see, I mean, we will use extensively while discussing quantum statistics, that is coming up in the next few videos or so. So I thought I could convey whatever I wanted to convey in this particular lecture. Basically, it was main aim was to convey the idea behind this degeneracy parameter, and once again I want to reiterate that this degeneracy parameter gives you a behavior of these gas molecules. Okay, how much it is, meaning ideal in this case. So if we try to study a gas or a system of particles through this Maxwell-Boltzmann statistics, how much we are in a position to predict its behavior correctly. So if degeneracy parameter is way larger than 1, then yes, we can use Maxwell-Boltzmann statistics, you can predict and it will work well. Okay, and if this parameter it gives you a checkpoint. Okay, so if it is not very large, or it becomes less than 1, then it will deviate from the ideal behavior of the from the ideal gas behavior. And in that case, if it is if degeneracy parameter is less than 1, then we say this strongly degenerate. Okay, and if it is slightly larger than 1, then we say this weakly degenerate. Okay, and if it is very much larger than 1, then we say it's a non-degenerate. Okay, so I hope I could convey the idea behind this, and we will see you in the next video on quantum statistics. Okay, thank you.